Hi everybody. Today I start the fourth lecture in the medical chemistry. Today my lecture starts with chemical bond. Chemical bond is a type of attraction between atoms. It is a strong attraction force between the certain atoms in substance, also we can say. It has a very high energy, around 100 to 1000 kilojoule per mole. We have a three type chemical bond: metallic bond, covalent bond, and ionic bond. Okay, metallic is with between the metals, okay, and covalent between the non-metals, and ionic between the cation and anion. Usually cation from metal, usually, and anion from the non-metal. Okay, we can have this. We will see the type of the cation and anion. It can be monoatomic or polyatomic. Also, we have octet rule. The tendency of atom to have 8 electron in the valence shell, because the valence shell, if we have 8 electron, it is a noble gas configuration. It is more stable, highest stability. It's very important for this stability. Metallic bond, as I mentioned, between the metals is the type of crystal of the metal. It is important because positively charged metal ions, it formed the nucleus or core of the atoms, and it delocalized valence electron cloud or electron sea. Then if you see in the center, we have a positive charge metals, and it's surrounded with the electron cloud or electron sea. As you see here, electron cloud or electron sea. Because of this reason, it can cause conductivity. For example, if we have electricity or heat for this metal, one electron comes inside, the other one can go out, because this electrons cloud is very important for the conductivity. Metallic bond, it is a type of electrostatic attraction between the metals, okay, and it is a cation and surrounded with the electron C or electron cloud. And the Weissend p and d orbital in the outer energy levels of metal overlap. And this one is allow the outer electrons to move freely throughout the metal, because in the metals p orbital is just free without electron, and the more free orbital and the jumping electron from the d orbital or s orbital to the p orbital can cause randomness and movement of the electron. And valence electrons do not belong to any of atom. It is for the whole of the metal. Physical property of atoms is, we have several properties, like for silver color, it has a conductivity for electricity and heat, but the melting point and boiling point can be, usually it is high, but some of them, like mercury, it is low, it is more different. And some of them hard, like iron, or some of them are very soft, like alkali metals like sodium, lithium, potassium. And usually metallic shine, and they are malleability and ductility, high tensile strength, and but as I mentioned, hardness or softness, it's usually not 100%. It's very hard. Some of them is soft, some of them is liquid, like mercury, very soft. Some is hard, like iron. And we finish the metallic bond, we go to the covalent bond. Covalent bond is between non-metal, as I mentioned. Chemical bond with is pair electrons, the share between two atoms, usually between two non-metals. For example, hydrogen has one electron. Hydrogen has one electron, and they can share each other and make this covalent bond. It's very important. We can show with a line, or we can show with a dot. 2 point is very easily. Then the covalent bond is the sharing electron between two atoms is mainly formed. As you see here, we can see, for example, HCl is the covalent bond between hydrogen and chlorine. As you see, the hydrogen has the one electron in its orbital s, but chlorine has the one electron in the orbital p, and the shading electron make also octet rule for the chlorine, and it is also the shape can be with s and p. But sometimes we can have a different type of the bonds in the covalent bond. Okay, we can have a single bond, double bond, triple bond. Okay, in the single bond, the bond length is high, energy low. Bond energy low. If we have a double bond, bond length decrease and energy increase. In the triple, we have a lowest bond length and highest energy, bond energy of bond. In the distance between two nuclei, we say it is the bond length and energy need for the break bond. It is the bond energy in the gas state. As you see here, between these two, it is the double and single bond oxygen. You see the bond length in the double is lower, and the energy in the double is higher. Formation of covalent bond in the hydrogen molecule. You see, if we have two hydrogens very far from each other, energy between effect, energy of attraction and repulsion between them is zero, because they don't affect any of it. But when we make close to each other, it start to attraction and energy go with the negative sign, okay? And when they are in the good, very favorable distance, the covalent bond form, and the bond length will be here for hydrogen 74 picometer, and the energy is the lowest in the negative, it has the highest stability. But if we have push again, they are together. If they are close to each other, and the repulsion suddenly increase, and this repulsion causes very high energy, which is they hate each other, and the energy go will be to the positive sign. And if they got very close to each other, they are very unstable, and in this situation, it is not usual thing that it is maybe in the laboratory can be happening in this situation. Now we can classify the covalent bond with the different electronegativity. If the difference of electronegativity of two atoms is the less than half, it is a non-polar covalent bond. Usually it is a symmetry, for example, the Cl2, H2, and they are non-polar, okay? But if the difference of electronegativity between half and 2.5, the bond is polar covalent bond, because the high electronegativity atoms, okay, it will be more negative, will be partial negative. The less electronegative will be partial positive, because have high electronegativity element or atom attract electron, and the electron mainly we can find around the high electronegativity atom. But if we have a difference of electronegativity more than 2.1, it is ionic bond. For example, NaCl, sodium chloride, which one of them is the cation, the other one is the anion. Then it is a cation, the second one is the anion. Okay, now we understand the main different part of the polar and non-polar covalent bond is here. Polar covalent bond, difference of the electronegativity between half and 2.1. The other type of the covalent bond is the coordinate covalent bond. In the coordinate covalent bond, both electrons can be donated by one atom. For example, this atom called donor. But the second atom must have the free orbital. If we have free orbital, then we can have this covalent, coordinate covalent. It usually make complex, for example, hem in the hemoglobin, or reaction of the proton with ammonia make ammonium. Now difference form other covalent bond important in the complex formation is very important. As I mentioned about single and multiple bound can be double and triple in the single bond. The bond is a sigma bond, okay? It is a covalent bond, the type of the bond is sigma, okay? But in the double and triple, the second, third bond are pi. For the formation of the bond, we require at least one sigma bond, okay? If we have a multiple bond, the second and third one must be pi. Then the first bond, one of the bond must be sigma. Okay, the pi bond is from the overlap of the p orbital. Now we go to the localized bonding. If we have electron pair and pi bound, they can delocalize in the molecule. Electrons of the bonding pair are spread over the number of atoms, and they can be very easily delocalized. For example, always we need the one pair electron, free pair electron, or non-bonding pair electron, and double and pi bound. This two is the requirement for the delocalized. As you see here, if this double bond, if this pair electron become double bond, this double bond become pair electron, we change the shape of the molecule, and if you see the localized, we can show with the double arrows is the mesomerical resonance effect. Resonance formula, resonance effect, it shows the localized bond between two atoms. It's very easy. And in the resonance, how we can show it. If you see here, we draw the same part, the same part in both of atoms. You see, it is here we have this area, and here we have this area, the same. Here single bond, the same. Oxygen is the same. The electron pair is the same. One single bond is the same, one oxygen the same, but here we have two electron, we have two paired electron here. As you see here, the other part is not the same. Okay, one paired electron. If you see here, from here we can understand this, the same part we draw here, not the same part. We can show here electron comes from these two bounds, and the pi bond can be delocalized between these two. For example, in the delocalization of the carbonate ion, if you see here, if again we can have here electron come here, it is a mesomeric effect we will study later. It comes here, and it can shape change to this one, or we can change the color. Maybe this color, if again come here and this come here, in this situation will be like this. And it can shows it is very easily double bond change between the carbon oxygens very easily. As you see here, all of the sigma bond in this molecule, always we have one sigma bond. But the pi bond we can easily delocalize between these two oxygen. Because 4 molecule has a -2 charge, we can write -2, or we can divide for 3 part, 1 part, 2 part, and 3 part. Because 2 divide for 3 part, it will be again -2. It is very easily, and we can see in this case. As you see here, the localization is very important, and is very helpful for the understand the mechanism of the reaction also. Theory of the covalent bond. For the theory of the covalent bond, we have two type of theory. The first one is valence bond theory, or VB, and second one molecular orbital theory, or MO. Okay? As you know, for the valence bond theory, individual atoms each have their own orbital. It's very important, orbital, and the orbital overlap to form bond very easily. It is independently, individually atom, and they overlap each other and make a bond, and it is independent and not related to each other. Okay, extent of overlap of atom orbital is related to bond strengths. Okay, it's very easy. Just we have orbital, atomic orbital, and they have overlap. We have make a bond. But in the molecular orbital theory, we say molecule as a collection of the positively charged nuclei in the middle, having a set of the molecular orbital, they are filled with the electron. Okay, the center is that we have a positive charge, we have a molecular orbital with the electron which is negative. Okay, similar to the atomic orbital. And usually, both of the mechanisms can be explained with the quantum mechanics we will see later. Oh yeah, here we can see the valence bond theory. As I mentioned here, atomic orbital overlap when the covalent bond is formed. We have it several times. If we have a sigma bond, we have, for example, hydrogen with hydrogen, just s orbital. It formation of ss orbital, two circular, and it make a sigma bond. 1s, 1p like hydrogen chloride, and 2p like 2 fluorine, like F2. It is F2. It is HCl and it is H2. It is from the valence bond theory we can explain it. But in the pi bound, overlap pi, for example, we can see if the 2 pi bound p orbital overlap will be pi bound. For example, if we have 1 sigma between 2 carbon, okay, for example, the second one, if we have a pi bound, it is overlap of these two p orbital. It is a pi bound. But this one, the others are sigma. Atomic orbital can combine during the bonding process, and the covalent hybrid orbital will be formed. It is more acceptable and more important, the hybridization, because in the hybridization usually we have a new molecular bond, new molecular orbital, and it is the hybridization, and it is important, and we have to know about this one. In the hybridization, all of the hybridized orbital are the same. In the hybridization, orbital hybridization is the concept of mixing of atoms, as I mentioned, the new hybrid orbital. What is the good things? For example, when we have a 1s orbital, which is a circular, and for example, when we have a 3p orbital, for example, px, py, and pz, in this case, we will form four same sp3, and it is very easily, as you see here. If I mention here what I mentioned here we have, for example, we have sp with mixing of s p orbital, sp2 mixing of s plus px and py, sp3 mixing of s plus px, py, and pz, and sp3d between s and 3p and 1d, and sp3d2 s plus px, py, pz and 2d. As I mentioned here, sp, it is a linear and the angle is 180. sp2 is the trigonoplanar and is 120 degree. sp3 is the tetrahedral and the angle is 109.5. And sp3d, I see here, we have two type of the angle, 102 and 20 and 90. And the last one, sp3t2, is the all 90 is octahedral, and sp3d is the trigonal bipyramidal. For example, for linear, we can example here we can see beryllium chloride. Beryllium is the group 2, and it has in the last valence it has a 2 electron, and we can make a bond with the 2 chloride here. Okay, and the angle is 180. BF3 is the group 3, and we can make a 3 bond, and methane carbon is the group 4, and with sp3 can make a 4 same bond. And other bond we can, for example, PF5, it is phosphorus group 5, and SF6 is sulfur from group 6, we can have these systems. Now I can show the one of them, BEF2, how the sp hybridization starts. As you see here, we have a beryllium fluoride. In the beryllium, we have a 4 electron, because beryllium is the 4 atomic number, 1s2, 2s2, okay? And it is a ground state. If the 1 electron jump from the ground state to the from S to the P, in this case it will be 1s2, 2s1, and 2p1. It is, we say, it is a promotion, okay, excitation, but promotion is more better. Now, if we hybridization happen between these valence shell electrons, we form 2 sp, 1 sp and 2 other, and 2 orbital is free. We don't care about it now. As you see here, this 2 electron can react with the fluorine, okay, shade electron between this F. As you see here, very important, when we have s orbital, p orbital, s is the circular, and if you use p is the double concave. And if you see here, after hybridization, we have a 2sp with 180 degree. And when we have a bound formation, and it will be between 2 fluorine atoms, and it make sp and 2 covalent bond. The other one is sp2 with the bf3. p is the atomic number is the 5, 1s2, 2s2, 2p1. If you see here, and the promotion happen or excitation, 1 electron jump from s to the p. As you see here, and now we have in the last valence shell 3, 1s2, 2s1, and 2p2, and here is the 2p1. And if we have a hybridization happen here between these 2, 3, from the 2s and 2p, and we have 3sp2. The shape is the trigonoplanar, and it can, and the angle is the 100 degree. The shape is the trigonal planar, and this fluorine can react. This electron can react with this fluorine, this one, and this one, and to make this bound very easily. As you see here, we can see the shape also here, 1s orbital, 2p orbital, and it make a sp2 trigonoplanar, angle is 120, It's very important and very nice. And thank you for attention. And I hope we can meet each other in the next lecture. And thanks a lot. And bye.